Hi everyone, in this video I'm going to show you how to numerically solve the Schrodinger's equation and apply it to any kind of a given potential. I'm going to divide the entire video into two distinct parts. In the first part, I'm going to show you the approach behind solving this kind of a problem. I'll show you the theoretical method or the approach that needs to be performed before we start executing the program. So if you understand this theoretical approach of how to solve the Schrodinger's equation, you can apply that to any kind of a computational platform, whether you are working in Scilab or MATLAB, or whether you are performing programs in C++ or maybe something else like Python. Once you understand this theoretical approach that I'm going to demonstrate in the first part of the video, you can apply that to any other kind of a computation platform. In the second part of the video, I'm going to use this theoretical approach to actually create a program where I'm going to apply it to some sort of a potential like a harmonic oscillator or a 1D infinite square well box. And I'm going to show you how we can obtain the energy eigenvalues, the wave function solutions, as well as the probability densities for those cases. So it's going to be a very, very interesting video. I'm Divya Das. This is For the Love of Physics, and let's begin. So the time independent Schrodinger's equation is given by minus h cut square upon 2m d2 psi upon dx2 plus v psi is equal to e psi. So here I'm going to show you how we can go about solving this equation. But first we need to define a range. Now I'm going to take the example of symmetric potentials. All right, so let's say that I have a given range in which some potential is defined. And I'm going to say that this entire range can be divided into two parts. So here this is the center, and here I have minus x, and here I have plus x. Okay, so I'm going to construct this particular approach where I'm going to solve the Schrodinger's equation for all the points in this kind of a symmetric potential. And now what is the nature of the potential, that I'm going to define later on, but I'm going to focus my attention to symmetric potentials only. So essentially, if we define a range, let's suppose from minus x to plus x, what we need to do is we need to solve the Schrodinger's equation at all the points in this particular range. So we need to solve the Schrodinger's equation, the time independent Schrodinger's equation, individually in all these points. Now, because ultimately we are going to use the help of a computer, so therefore I just need to structure the concept in a proper way, and then later on we can optimize the various parameters like the number of points, step size, etc., etc. So let's say the potential is defined in this region, okay? And because the potential is defined in this region, the particle's wave function solution will also exist in this region. And my entire job is to find out the nature of that particle's wave function solution or eigenfunction solution. But before we start doing that, let's look at the number of divisions. So let's say I divide this entire range into n number of points. So I'm going to start with I is equal to 0, 1, 2, 3, 4, and go on till n minus 1 and n. So essentially I have divided this range. In this range I want to solve the Schrodinger's equation. I have divided into n number of points. If I look at the step size, what is the step size here? I'm going to call the step size as d. So what is d? d is nothing but xn minus x naught divided by the total number of points. Now, another thing that I'm going to assume here is that the range is so large, or the nature of the potential is such that the endpoints, or at the endpoints, the wave function solution is actually 0. This is a very important boundary condition that I'm going to start with. So whatever nature of potential I end up taking later on would be such that the wave function solution should go to 0 at the endpoints. This is a boundary value problem, okay? So it means that if I define the wave function, let's suppose at this particular point, if I define the wave function at psi x naught, then that should be equal to 0. And if I define the wave function at this particular point, that is psi xn, then it should be equal to 0. Even the derivatives of the wave function should also come out to be 0. Now these are the assumptions that I'm going to start with, that I have a range from minus x to plus x in which the potential is defined. The potential is symmetric with respect to the x-axis, and the nature of the potential is such that the wave function of the particle vanishes at the endpoints. Based on these assumptions, let's begin. So I need to write down the time independent Schrodinger's equation for every single point. So let's suppose I write this as minus h cut square upon 2m psi double dash plus v psi is equal to e psi. I need to make one thing clear, that these functions are functions of x. So this is a function of x. V, which is the potential, is also a function of x. Psi is a function of x. E is the energy eigenvalues here. All right. Now the thing is, how do I solve a second order differential equation that contains this second order derivative? Psi double dash is a second order derivative of psi. To do that, I'm going to make use of what is known as finite difference method. Finite difference method says that if you have a function, its second order derivative is equal to the value of the function at x plus, let's suppose, step size d minus twice the function at x plus the function at x minus d upon d square. So this is a finite difference method where it gives us a formula to compute the second order derivative of any given function. Here we are interested in essentially the second order derivative of psi. So this can be written as psi at, let's suppose, if I want to find out the second order derivative at xi, then this is nothing but psi at xi plus 1 minus 2 psi at xi plus psi at xi minus 1 upon d square. All right. So this is merely a numerical method to figure out the second order derivative of some kind of a simple single valued continuous function. So if I apply this onto the Schrodinger's equation and evaluate it at all the points, because at I is equal to 0 and I is equal to n, we do not need to perform the Schrodinger's equation because the solutions are already known. At I is equal to 0, which is a left hand side n point, the wave function solution is already 0. And at I is equal to n, which is the right hand side endpoint, the wave function solution is already this 0. So I don't need to perform the Schrodinger's equation here. I, however, need to perform the Schrodinger's equation for all these intermediate points from 1 up to n minus 1. Here I need to perform every single Schrodinger's equation. So if I do that, let's start with for I is equal to 1. So for I is equal to 1, the time independent Schrodinger's equation become. Okay, now if I substitute psi double dash here based on the finite difference method, I get minus h cut square upon 2m. Here I should get, so this should come out to be 2m d square, and here I should get psi x2 minus 2 psi x1 plus psi x0. Let's separate the right hand side from the left hand side. Okay, I hope that everything is visible to you. So here, of course, psi x0 is 0 because that's the left hand side endpoint. So therefore the expression simplifies to minus psi x2 plus twice psi x1 plus 2m d square upon h cut square vx1 psi x1 is equal to 2m d square upon h cut square e psi x1. I can simplify this further by saying that 2 plus 2m d square upon h cut square vx1 whole multiplied by psi x1 minus psi x2 is equal to 2m d square e upon h cut square e psi x1. Please note that psi x1 is essentially the wave function solution at x1. So we are trying to solve the Schrodinger's equation at the location x1, and this is the Schrodinger's equation for that. If we solve it, we should find out what psi x1 is. Now, if I write down the Schrodinger's equation for, let's suppose, I is equal to 2, then I should get another equation similar to this. So for I is equal to 2, if I write everything down, I should get something like this. If I substitute psi double dash x2 with the finite difference formula, then this will further become I hope that you are able to see these lines. So here I can further simplify this into this should be psi x1 and x3, by the way. Okay, psi x1 and psi x3 here. So this becomes, so this is the equation we get for the point x2. So I need to do this repeatedly over and over again for all the points involved. For psi x3 also I'll get something similar. So let me just write it down. So if you look at these equations, you probably see something similar. The equations are kind of similar. We'll see what that similarity is. For let's suppose for I is equal to 3, you will get an equation that looks something like this. And on and on. All right, this will go on. So we will have to actually do this individually for every single point in this range, for x3, for x4, up to xn minus 1. So let me write down the last equation. So the last equation for I is equal to n minus 1, what should it look like? It should look something like this. So you see this in the last equation, it contains this particular term psi xn, which again is 0 because that is the nature of the boundary condition. So essentially we will get n minus 1 equations. So this is equation number 1, which we get here, and then we get equation number 2 for point number x2, we get equation number 3, and then on and on up to equation number n minus 1. So what we have is n minus 1 simultaneous linear equations that need to be solved to come up with a solution of the Schrodinger's equation for this given range. I want to solve the Schrodinger's equation in this given range, right? I want to find out the energy eigenvalues of the particle in this range, the eigenfunctions solutions, and the probability densities. So I have to solve the Schrodinger's equation at every single point. Now, even though it looks very complicated up till this point, it's going to become much more simpler now. How? Well, let me just write down these equations one by one. You will see how simple it becomes. So the first equation we obtained was this equation for I is equal to 1. Let's copy this, and I want to show you how everything looks together. And this is the first equation. The second equation was for I is equal to 2. Let's copy this, and let's put it just right below here. And the third equation was this equation. Let's copy this and paste it here. And the last equation is this one. Let's copy this also and paste it here. So essentially for the given range of x going from minus x to plus x, for I is equal to 0, 1, 2 up to n minus 1 n, we have these equations: equation number 1, equation number 2, equation number 3, equation number 3, 4, on and on up to equation number n minus 1. So now how do we go about it? These are a large number of equations, right? Well, we can structure these simultaneous linear equations in the form of a matrix, and we can make a matrix eigenvalue problem out of it. How do we do that? Well, you see here, the first equation contains psi x1, which is the wave function solution at x1, and psi x2, which is the wave function solution at x2, right? The second contains psi x1, x2, and x3. Third contains x2, x3, and x4. So if we construct a matrix eigenvalue problem, the eigenvector will contain these values: psi x1, psi x2, psi x3, psi x4, something like that. So what we can do is, I can create this kind of a matrix. Let me just write down the matrix here. It looks a little difficult when I write it down analytically, but when we perform it using the help of a computer, it's going to be much more easier. Okay. So here I can write these eigenfunction solutions or wave function solutions: psi x1, psi x2, psi x3, and on. You have psi x n minus 2, psi x n minus 1. So let's look at the first equation. If we look at the first equation, what do we see? We see that the coefficient for psi x1 is 2 plus 2m d square upon h cut square vx1. So let's just write that here. 2 plus 2m d square upon h cut square v of x1, which is a potential at the point x1. And then what is the coefficient of x2? Minus 1. So here I get minus 1. And what are the coefficients of x, psi x3, psi x4, etc., Nothing. They are all 0. Okay, they are all 0. Now, if we look at equation number 2, and in the right hand side we have 2m d square e upon h cut square. So here we have 2m d square e upon h cut square. D is the step size and E is the energy eigenvalues. Okay. So let's look at equation number 2. Here, what is the coefficient of psi x1? It's minus 1. So here we will get minus 1. What is the coefficient of psi x2? Well, this is the same as this, 2 plus 2m d square upon h cut square v at x2. And what is the coefficient of psi x3? It's minus 1. So you'll have minus 1 here and the rest are all 0. Similarly, if you look at equation number 3, you will also get something like this. What is the coefficient of psi x2? Psi x1, it's 0. Coefficient of psi x2, it's minus 1. Coefficient of psi x3, it's 2 plus 2m d square upon h cut square vx3. And what's the coefficient of psi x4? It's minus 1. And then on. So if you go and construct all these elements in the matrix, what you will find is that in the second last row, you will get a minus 1 here and a minus 1 here, and in between you will have 2 plus 2m d square upon h cut square vx n minus 2, and in the last row you will have minus 1 and 2 plus 2m d square upon h cut square vx n minus 1. I hope this is clear and it's not causing any confusion. Just keep in mind that this particular term 2 plus 2m d square upon h cut square vx, these are all the diagonal elements. These are all the diagonal elements, and right neighboring to the diagonal elements, these are all minus 1. You see, these are all minus 1. That's it. Everything else is 0. Do you see that? Now it becomes a little bit simpler, that all the diagonal elements are this particular term 2 plus 2m d square upon h cut square vx, and all the neighboring up and below the diagonal are minus 1. Everything else is 0. So this therefore is the necessary matrix that we are interested in. Okay, so if I say that this entire thing can simply be written as some matrix A. So if I say that this is a matrix A and this is the eigenvector, which is the wave function solution that we're interested in, I say that this is x and this is some constant. I'm going to call this as lambda, and this is the same as capital X. So this is a matrix eigenvalue problem. This now becomes a matrix eigenvalue problem. If I can only find out the eigenvalues of A, from there I can find out the nature of the energy eigenvalues, right? Multiplied by some constant. And if I can find out the eigenvector of A, now that eigenvector is nothing but the wave function solution at every single point. So wave function solution at here, here, here. So this is basically the wave function solution across the range of x. Alright, now we already know the wave function solution at x0 and xn, which is 0 by the way. For the intermediate range, this eigenvector will contain the wave function solution. So that is it. So all we need to do, if you are familiar with some kind of a computational sort of platform or programming language, is to construct this matrix. And if you're able to construct this matrix and find out the eigenvalues and the eigenvectors of this matrix, the eigenvalues will give you an idea about the energy eigenvalues of the particle in that particular potential, and the eigenvectors will give you an idea about the nature of the wave function and the probability density of any particle in that particular potential. So this is the theoretical approach or the construction of the problem before we go into the programming. So let me just quickly give you a revision of what we have done. We need to solve the time independent Schrodinger's equation in a given range of x for every single point. So let's say the potential, which is a symmetric potential, is defined in this range of x. I need to solve the time independent Schrodinger's equation in every single point. So what we do is we divide this range into n number of points with step size d. And I also make the assumption that at the end points, the wave function is actually 0. The nature of the potential is such that the wave function is actually 0. If you have some difficulty with the nature of the potential, you can always take plus x and minus x to tend towards infinity, because for a realistic wave function at infinity it always goes to 0. So I just apply the Schrodinger's equation for point I is equal to 1, I is equal to 2, I is equal to 3, and then I apply the finite difference method. The finite difference method gives us a numerical computational method for figuring out the second order derivative of a function. So I apply it, I come up with these equations: equation number 1, equation number 2, equation number 3, and up to equation number n minus 1, and then I construct this matrix eigenvalue problem based on that information. So all we are going to do now is I'm going to shift to Scilab, and my job is to construct this matrix and find the eigenvalues and the eigenvectors, and from there on I can figure out the nature of the wave function and the probability densities of the potential involved. So let's go ahead to the next portion of the video. Alright, so here I have Scilab. Now you can do everything that I have just now described in any other programming language also, in MATLAB, maybe in C++, but I'm going to show you how to do it in Scilab. Now I have these kind of constants here. We need the mass of the particle. So let's suppose the mass of the particle is the mass of the electron, and h, I'm going to use the I'm not going to use the SI units. I'm taking the mass of the electron in electron volt. So the mass of the electron in electron volt is given as 0.5 mega electron volt. So 0.5 into 10 to the power 6 electron volt. Now this is the Planck's constant in terms of electron volt angstrom. This is actually not the Planck's constant. This is Planck's constant, that is h cut c. So the constant that I am taking here is h cut c, which is 1973 electron volt angstrom. So the distances that we are going to deal with therefore will be in angstrom and not in meters. And the mass of the electron that I am choosing is 0.511 mega electron volt upon c square. Alright, so instead of h cut, I'm going to use h cut c. So keep that in mind. Alright, the reason I'm not choosing the SI units is the SI units Planck's constant is a very small number. It contains the order of 10 to the minus 34. So there's a possibility that during computation, the program might round off and give us an incorrect result. Therefore, I'm choosing these particular units. All right, now let's choose a range. Okay, now let's suppose I'm going to go from minus 5 to plus 5. So let me choose a range of minus 5 angstrom to plus 5 angstrom. I'm dealing with microscopic dimensions. So let's suppose an electron is in this particular region. Okay, so what is this distance? This distance is basically 10 angstrom. Okay, I'm going to call this as A is equal to 10 angstrom. And let me take n first just to construct the program as 10 maybe. Or let's take it 5. So D is going to be essentially equal to 10 angstrom divided by number of points. So let me implement that. All right, so now let me define the x-axis. So what is the x-axis? The x-axis is going from minus a upon 2 with a step size of d to plus a upon. So now I need to basically construct this matrix. But to construct this matrix, I need the potential v. So what I'm going to do is I'm going to construct a function for this potential, so that I can evaluate the potential at every single point along the x-axis. So let's suppose y is equal to vx. Okay. Now, what kind of a potential you want to take first? let's take the harmonic oscillator. Okay, I'm going to take the harmonic oscillator, and I'm going to change the potential a little bit later on, but let's consider the harmonic oscillator problem first. Now I want to construct this matrix. Yeah, so what is the size of this matrix? So you see the size of the matrix is n minus 1 times n minus 1. Okay, because I'm evaluating at all the intermediate points. In the x-axis, I have x0 to xn, but because I'm not evaluating the Schrodinger's equation at x0 and xn, I'm only evaluating in the intermediate points. Therefore, the size of the matrix comes out to be n minus 1 cross n minus 1. So let's bring the editor somewhere here so that I can make a comparison. Okay. I hope that you can see this. Let's keep it like this, okay? So if I want to construct this matrix, so I'm going to use a for loop here. Let's suppose for I is equal to 1 to n minus 1. I've already defined what n is. So I want to specify the diagonal elements I comma I. So what are the diagonal elements? A I comma I. Well, they are, okay, let me take it to the top, okay, just so that you can see everything here clearly. So I want to specify the diagonal elements first. So the diagonal elements are 2 times 1 plus m d square upon h cut square, which is h here, which is multiplied to the potential. So this entire term is multiplied to the potential. The potential is defined with a function. I have defined it as a function Vx. So I'm going to call this as V of xi. All right. Now this should be the nature of the diagonal elements. Now the thing is, what is Vxi? Vxi is essentially the potential which is evaluated at every single point along the x-axis, but I also need to define xi therefore in this particular situation. So xi is equal to, now I have already defined the array x, but I need the individual points, which is basically x with index I. Because I am ignoring the extreme left hand side point, I need I plus 1 here. Okay, so for I is equal to 1, this is going to give me the second element from x-axis, because the first element is the left hand side boundary point, which I'm not evaluating in this matrix. Further, the neighboring lines, the above the and below the diagonal are minus 1, that I can implement here like. Alright, so I've constructed this matrix. Let's check whether the matrix is making any sense or not. Let's go to the console and check if the matrix is making any sense or not. Well, you see, yeah, there are the diagonal terms and the neighboring terms, but this last term, this comes out to be 0. The reason being that my code needs to, these two lines need to perform only for those cases for which the index is less than n minus 1. So basically, if I is less than n minus 1, only then perform this n. This should make the matrix the way we want it. So now let's check A. All right, you see this matrix? So these are the diagonal terms and the neighboring terms are minus 1, everything else is 0. So this is the kind of matrix that we are interested in, and that's it. We have constructed the matrix successfully. So now all we need to do is need to find the eigenvalues and the eigenvectors. And to do that, we have an inbuilt command in Scilab. There's an inbuilt command in Scilab to find out the eigenvalues and eigenvectors. The eigenvector, let's suppose I call it x, and the eigenvalue, let's suppose I call it lambda. This is equal to spec of capital A. So spec is the command in Scilab to find out the eigenvalues and the eigenvectors. Once I do that, I run it, I should get the solution basically. So we have the solution, we just need to write it down appropriately. So let's look at what x is. If I go to the console and type capital X, so essentially I get these columns. You see, I have divided the x-axis into 5 points, right? Or rather 4 points, excluding the boundary points. So I get these column vectors. So first represents psi x1, second represents psi x2, third column represents psi x3, and the fourth column represents psi x4. So psi x psi 0, then this is nothing but capital X, the first column. So this is first column, and that is for the ground state. Psi 1, that is capital X, the second column, and the second excited state is the capital X eigenvector, third column, and similarly the higher ones. Now there is one more thing I want to keep in mind, which is, let's go back to our original discussion. What we did here was the potential is defined in this entire range, but I did not solve the Schrodinger's equation at the boundary points. The reason being, I already am assuming that the wave function solution is 0 at the extreme points. The wave function solution at x0 is 0 and at xn is also 0. So therefore, when I applied this matrix, which is essentially for this intermediate points, the size of that particular wave function is defined only for the intermediate points, right? So to make a complete case, I need to include these 2 points also in our solution. So how do I include these 2 points? I just include 0, 0, that's it, because that is the assumption we started with. So let's suppose this is psi 0, right? What is this? This is a column vector, or this is a column matrix. So I introduce two separate rows at the end and at the beginning containing 0. So then this is going to be a complete column vector with a very initial element and the end element as 0. Let me just show it to you, okay? So if I copy and paste it in the console, I should get something like this. You see this? So this is a psi x naught at the left hand side boundary point, and this is psi x naught at the right hand side boundary point. So this is the ground state wave function at the left hand side boundary point and the ground state wave function at the right hand side boundary point, because these are the assumptions I started with. Intermediate, that depends upon the nature of the Schrodinger's equation. So let's make these modifications further to the others also. Alright, so now this is it. We have constructed the matrix that is necessary for us, and we have given the nature of the potential, and we have come up with the wave function solutions for the ground state, first excited state, second excited state, and third excited state. Let's plot them and see have we got anything that makes sense or not. So let's just apply the plot command. In the x-axis we have psi 0, and again in the x-axis I want to plot psi 1. So if I give these plot commands and run it, yeah, all right. So I get something that looks like this. The reason being that this range of distance that I've taken, I've only divided into, or rather 6 points, right? 4 intermediate and 2 boundary points. Now, the beauty of using a computer is that it can perform these repetitive calculations n number of times. I can take this region and divide it into extremely small number of points so that the accuracy of the results are going to improve. So here, instead of taking 5, all right, points here, and it was 6 including 0 by the way, and let me take 100. If I take 100, then that should considerably improve the nature of the results. There you have it. These look like that they are the solutions of a harmonic oscillator, but let's wait for a little bit. Let me just show you something. Let me give a little bit of a plot property here. All right, by changing the plot properties, it looks a little bit better on now. So clearly the blue one should be the ground state, I think, and the green one should be the first excited state, and the cyan colored one is the second excited state. Okay, by the way, I should have written 1, 2, 3, 4 here. Okay, let's write 4. Now let's look here. I missed out one of the solutions. So the blue is the ground state, the green is the first excited state, the red is the second excited state, and the cyan colored is the third excited state. Let me apply the legend command to differentiate between all of them. All right, so you should be able to see the, okay, I want to put it somewhere else, let's suppose, or yeah, let's keep it to the left hand side corner. 3. All right, now these are the wave function solutions. Let me go ahead and demonstrate the probability densities. So for the probability densities, I am basically interested not in psi 0, but in psi 0 inner product with psi 0, right? So inner product is given by dot star. Okay, this will give us the inner product of psi 0 and psi 0. Or I think I should just say dot to the power 2. That is more than sufficient. Okay, if I run this now, let's see. Okay, it seems like I'm getting something, but I want it to look a little bit better. I want it to look like how you guys see it in the traditional books. To do that, I want to separate out all the probability densities in the vertical axis. So let me add some kind of a term to it. So whatever the maximum height of the ground state is, I'm going to add it to every single point. So let's see z axis or z as a variable, the maximum height of, let's suppose, psi, the ground state probability density. Okay, so I'm going to add it to every single term so that it shifts in the vertical axis so that I can see it in a better diagrammatic representation. So plus z here, and here I have plus 2z, and here I have plus 3z. I think this should work. This should separate the probability densities in the vertical axis so that I can see them separately. All right, I can see them separately, but I think I have taken a wrong term here. This should have been 2. Let's check. All right, now they are intersecting. Let me take a small increment here, plus 0.01. Let's see. I'm only creating a better diagrammatic representation here. Okay. All right. So these are the probability densities of the ground state, the first excited state, the second excited state, and the third excited state of a harmonic oscillator potential. Let me also plot the potential together so that we can get the beautiful graph that is usually shown in books. Okay. So let me also plot the x versus vx. This one. If we do that, then we should also see the potential. Now, of course, the nature of the potential is that units are different. Now, I don't want the potential to sort of zoom out of the graph. So I only want a diagrammatic representation. So let me just sort of normalize it by dividing it with some kind of a large number so as to get a better diagrammatic representation. I think the one number I used is 150. All right, let's see what we get. All right, there you have it. Looks beautiful, just like you see it in various books. The blue line is the ground state probability density of a particle in a harmonic oscillator potential well. The green line is the first excited state probability density for the particle in a harmonic oscillator potential well. The red and the cyan are the second and the third excited state probability densities. We can go on and figure out the other kinds of probability densities for higher excited states as well. Now that looks nice, isn't it? So we have been successful in constructing the mathematical approach as well as in writing the program to come up with this answer. It looks very, very beautiful, isn't it? We can go a step further and do for other potentials also. So for example, instead of a harmonic oscillator, if I want an infinite square wave potential. So an infinite square wave potential basically has zero potential in the given range, and beyond it, the wave function is automatically zero. So for that, the only modification I need to do here is plug in 0. If I do that, I should get the solutions for the infinite square wave potential. This is the solutions for the infinite square wave potential. You see that? Because here in this range, there is a wall at x is equal to -5, and here at x is equal to +5 there is a wall. This is an infinite potential wall. The wave function goes to 0. In the middle you have the ground state, the first excited state, the second excited state, the third excited state. You see, the program seems to be so simple, right? It's just a couple of lines, 22 lines I have here. If you ignore the first 2 lines, that's just 20 lines of code. With 20 lines of code, I have created a program that can actually solve the Schrodinger's equation for a given range of x-axis for any kind of a potential, as long as it is symmetric with respect to the x-axis. Now, we can experiment with this. You see, analytically, we can solve the harmonic oscillator, infinite square wave potential, but what if we have other kinds of potential that we might not be comfortable solving analytically? We can do that also here. So, for example, what if let me take some random potentials, okay? Let's say that I choose x to the power 4 or something like that, some n harmonic oscillator, okay? If I choose something like that, Let's not plug in the potential graph. Let's just look at it like this. Okay, it also contains these kinds of solutions. For x to the power 4, what if I have something like absolute value of x, so basically a triangular potential, right? Inverted triangular potential. So you see this is the nature of the potential. Well, that is the nature of the solution. What if I choose the potential to be like a slope? Okay, the ground is like a slope. If the ground is like a slope, then what's going to happen? So if I take x here, the ground is going to be like a slope, and then you see the wave function of the ground state is sort of probability density is concentrated here, where the slope is going downwards and the rest are also slightly deviating from it. So I can come up with any kind of a nature of potential. If I take, let's suppose, cos x, okay, cos x, okay, I'm just experimenting with different potentials. If I take cos x and run this, then I'm going to get something. So this is the nature of the potential, and basically it's a 0 at the -5 +5, and these are the nature of the ground state and first excited state and other higher excited states probability densities. There is also a double well potential or an inverted double well potential. Let me apply that also. I have here 0.05 times x to the power 4 minus x square. This is an inverted double well potential. This also has solutions which are slightly different from the harmonic oscillator and others. Here the ground state contains these two peaks slightly above the sort of valleys that we basically have. So there you have it. This is in fact a solution for the inverted double well potential. Also, if you are interested in figuring out the eigenvalues are very easy to obtain. You see, the eigenvalues are essentially what? The eigenvalues are essentially E, right? What is E? E is essentially equal to h cut square upon 2m d square multiplied by lambda. So if I implement that into the program, I should get the energy eigenvalues also. The eigenvalues are actually the diagonal elements of this matrix E that we get. Of the lambda that we get. So therefore I've written it here. So if I display for any kind of a potential, I can display the energy eigenvalues for, let's suppose, E11. So 1 comma 1 is going to give us the ground state energy eigenvalue for any kind of potential. So whatever potential I have here, it's going to give us, if I go to the console, it's going to give us this value, right? It's going to give us this particular value. So you can check that for any kind of a potential that you're working with. So this program does a complete solution for the Schrodinger's equation for any kind of a potential that is symmetric with respect to the x-axis. And you can also find out the eigenvalues by writing E11 for the ground state, E22 for the first excited state, E33 for the second excited state, and on and on. So there you have it, a solution to the Schrodinger's equation done numerically and performed via Scilab. So I hope you enjoyed this video. I am Divya Jyoti Das. This is For the Love of Physics. I will see you in the next video. Thank you very much.